Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the annals of theoretical physics, there exist moments of such profound conceptual audacity that they seem to come unstuck from their own time, functioning less as contributions to a contemporary dialogue and more as prophetic whispers to a future generation of thinkers. William Kingdon Clifford's 2875 paper, presented as an abstract to the Cambridge Philosophical Society under the title On the Space Theory of Matter, is the quintessential example of such a moment. In a mere handful of paragraphs, Clifford outlined a vision of the universe so radical, so elegantly unified, and so far removed from the established physics of ether, atoms, and forces, that it remained largely a curiosity for nearly half a century. This essay undertakes a rigorous, section-by-section evaluation of the specific claims, internal logic, and conceptual framework presented in Clifford's work. The analysis will proceed sequentially through the paper's core propositions, assessing the intellectual foundations, the coherence of the hypotheses, and the sheer ambition of its attempt to reduce all of physical reality to the dynamic geometry of space itself, revealing the mind grappling with the ultimate nature of existence through the language of pure mathematics. Section 1. The Riemannian foundation and the empirical nature of geometry. Clifford commences his argument by explicitly situating his entire thesis upon the foundations laid by Bernhard Riemann in his 1854 habilitation lecture on the hypotheses which lie at the basis of geometry. The primary claim Clifford inherits and champions is that the character of space is an empirical question, a matter for physical inquiry, a departure from the Kantian view of geometry as an a priori intuition. Clifford's evaluation of Riemann's work is absolutely presented as the necessary and sufficient precondition for his own physical speculation. The internal logic of this starting point is impeccable. For Clifford to propose that space has physical properties that constitute matter, he first requires a conception of space that is flexible and whose properties are discoverable. Riemann's geometry provides precisely this conceptual toolkit. It introduces the mathematical framework for describing a space of any number of dimensions whose curvature can vary from point to point. By adopting Riemann, Clifford is claiming that the familiar Euclidean geometry, with its unwavering axioms of parallel lines and flat planes, represents a special and perhaps merely approximate case. The deeper claim being evaluated here is that the very axioms of geometry are contingent upon the physical structure of the universe. Clifford's acceptance of this is total. He uses Riemann's work to transform space from a passive, absolute, and empty stage of Newtonian void, in which the drama of physics unfolds into an active, dynamic, and substantial medium that is itself the sole actor. The validity of Clifford's initial SEB, therefore, rests entirely on the philosophical and mathematical plausibility of the Riemannian program. From a 1875 perspective, this was a bold and speculative alignment. While Riemann's mathematics was admired in professional circles, its application to the physical world was an exotic idea. Clifford's claim, evaluated internally, is that the most advanced understanding of pure geometry provides the most truthful language for describing physical reality, a position of profound mathematical Platonism. Section 2. The core hypothesis of spatial curvature as substance. The second major proposition in Clifford's abstract contains the central pillar of his entire theory. He proposes, with remarkable directness, the idea that small portions of space are in fact of a nature analogous to little hills on a surface which is on the average flat. This assertion must be evaluated on multiple levels. First is the power of its analogy. The image of little hills on a flat surface provides an intuitive entry point into the esoteric concept of intrinsic curvature in 3 dimensions. The hills are localized regions where the geometry deviates from the Euclidean norm, and the surface which is on the average flat corresponds to the observation that, on a large scale, space appears to obey the familiar rules of Euclid. The claim's deeper physical substance is its radical ontology. Clifford is positing that these geometric variations, these hillocks of curvature, are not disturbances in a substance, they are the substance. What his contemporaries would call an atom of matter, Clifford identifies as a region of intensely curved space. This is a claim of ultimate reduction. It eliminates the long-standing dualism between space and matter, a foundational concept of physics from Democritus to Newton. In Clifford's model, there is only one entity space. Matter is a manifestation of its geometric properties. Evaluating this claim requires assessing its explanatory power. As a hypothesis, it is extraordinarily parsimonious. It accounts for the existence of discrete particles of matter without needing to invent a new type of fundamental particle. Instead, it leverages the already existing concept of space and imbues it with dynamic potential. The mechanism, he implies, is one of geometric form. The stability, identity, and properties of a particle of matter would, in this framework, correspond to the specific, stable configuration of a particular knot or bump of curvature. The claim is coherent, self-contained, and philosophically elegant. Its primary weakness, from a standpoint of internal critique, is its complete lack of a quantitative dimension. Clifford provides the what but gives no indication of the how much. There is no formula connecting a specific measure of curvature to a specific mass or charge. The claim is a brilliant piece of physical intuition, a qualitative blueprint for a new physics, presented without any of the mathematical equations that would be necessary to build the structure. Section 3. The geometric interpretation of motion and matter. Following his static description of matter as curved space, Clifford proceeds to his dynamic claim, arguing that this variation of the curvature of space is what really happens in that phenomenon which we call the motion of matter. This is perhaps the most subtle and profound assertion in the entire paper. He is proposing a redefinition of motion itself. In the classical view, motion is the traversal of an object from one point in space to another over time. Clifford's claim dissolves this picture. If matter is a region of curvature, then the motion of matter cannot be the movement of this region through a separate, static background space. Instead, motion must be the propagation of the state of curvature itself. One can visualize this as a ripple or a wave crest moving across the surface of a pond. The wave moves, but the water itself only moves up and down. Analogously, in Clifford's universe, the hillock of curvature that constitutes a particle moves by transferring its geometric state from one adjacent region of space to the next. The particle does not move through space, it is a process of geometric change that propagates across the spatial manifold. The evaluation of this claim reveals its deep consistency with the preceding one. It is the logical consequence of identifying matter with geometry. If matter is a feature of space, its motion must be a dynamic process within the geometry of space. This idea carries tremendous intellectual weight. It suggests that the laws of motion, the principles of kinematics and dynamics, could ultimately be derived from a deeper set of geometric laws governing the evolution of curvature. A particle following a specific trajectory is, in this view, a wave of curvature evolving according to some fundamental geometric wave equation. The true elegance of this claim is how it unifies the concept of a particle's existence with its movement. An object and its trajectory become two aspects of the same underlying geometric process. The critique of this section mirrors the critique of the previous one. While the concept is philosophically compelling and internally consistent, it remains a purely qualitative vision. Clifford offers no principle, no variational principle or differential equation that would govern this propagation of curvature. He has described the phenomenon he wishes to explain in a new language, but he has yet to formulate the grammar and syntax of that language. He has substituted one mystery, the motion of particles, with another, the law of propagation for spatial curvature. Section 4. The assertion of universal geometric monism. Clifford then elevates his theory to its ultimate, a encompassing conclusion with the breathtakingly simple statement that in the physical world nothing else takes place but this variation. This is the moment the abstract transitions from a specific theory of matter to a comprehensive cosmology and a declaration of profound physical monism. The claim must be evaluated as a statement of total unification. With this single sentence, Clifford proposes to sweep away the entire conceptual apparatus of 19th century physics. The concept of force, particularly the mysterious action at a distance of Newtonian gravity, is eliminated. In its place, the apparent attraction between two bodies would be a consequence of them both following paths of natural propagation within a geometry that is mutually influenced by their presence. The fields of electromagnetism, which Maxwell had recently codified, would likewise need to find their explanation as some form of geometric torsion or strain within the spatial manifold. The luminiferous ether, that problematic or pervading substance required for the propagation of light, becomes entirely superfluous. Light matter, would simply be another species of geometric disturbance propagating through space. The internal claim is one of absolute ontological parsimony. Clifford asserts that a single actual dynamic, geometric space is sufficient to explain the entirety of physical phenomena. This is the theory's most audacious and, from a contemporary perspective, its most vulnerable point. To claim that electricity, magnetism, gravity, and the very substance of matter are all emergent properties of a single underlying field of geometry is a hypothesis of titanic scale. The argument's strength is its promise of ultimate elegance and unity. Its overwhelming weakness is the complete absence of any demonstrated connection between the proposed geometric variations and the highly specific, mathematically described phenomena of the real world. How could a simple curvature account for the difference between a positive and a negative electric charge? How would the inverse square law of gravity emerge from the rules governing this geometry? Clifford's claim functions as a philosophical manifesto, a grand research program proposed for future generations. It is a statement of faith in the power of geometry to serve as the ultimate bedrock of reality. The evaluation must conclude that, as a piece of 1875 physics, the claim is empirically empty. Yet as a piece of philosophical and theoretical vision, it is astonishingly fair. Section 5. The acknowledgement of speculation and the search for a mechanism. In a fascinating denouement to his radical proposals, Clifford tempers his declarations with a measure of intellectual humility and forward-looking cautiousness. He acknowledges the speculative nature of his space theory of matter and considers its relationship to other ongoing physical investigations. He mentions the vortex theory of atoms, proposed by William Thomson, Lord Kelvin, which imagined atoms as stable, knotted vortices in the ether. Clifford's claim here is a careful positioning of his own idea. He seems to suggest that his theory might provide a deeper foundation for such models, remarking that the study of space curvature might reveal possibilities for the kind of complex, stable, knot-like structures that the vortex theory required. This section serves as a crucial piece of self-evaluation. Clifford is effectively admitting that his grand geometric vision lacks a concrete mechanism. He is aware that the hills he described need a more rigorous mathematical characterization to explain the properties of matter. His allusion to his own work on biquaternions, a complex number system extending quaternions, can be interpreted in this light. He was actively searching for the right mathematical language, the appropriate algebraic structure, to describe the physics of his geometric universe. Biquaternions, with their properties of rotation and scaling, appeared to him a promising tool for describing transformations and strains in space. This final part of the abstract is an evaluation of his own theory's incompleteness. He recognizes that his claims, while philosophically coherent, require a mathematical engine to become a predictive science. His intellectual honesty is palpable. Having proposed a universe built from nothing but geometry, he concedes that the specific rules of that geometry, the very details that would connect his vision to experimental reality, remained elusive. This final claim, therefore, is an admission of the gap between his physical intuition and the available mathematical technology. It frames his entire paper not as a finished theory, but as a signpost pointing toward a new, undiscovered continent of thought, for which the maps were yet to be drawn. He had, with a certain intellectual grace, identified the destination, while acknowledging his inability to chart the conclusion. The enduring significance of William Kingdon Clifford's On the Space Theory of Matter is located precisely in the tension between the profundity of its claims and the almost complete absence of a supporting mathematical or empirical framework. A direct evaluation of its internal arguments reveals a structure of impeccable philosophical logic built upon a foundation of pure, unproven hypothesis. Its initial claim, grounding physics in the empirical, Riemannian view of geometry, was a necessary and brilliant appropriation of advanced mathematics. The subsequent claim said matter is localized curvature, that motion is the propagation of this curvature, and that all physical laws derived from this single geometric process unfold with a beautiful and compelling coherence. The theory is a masterpiece of conceptual unification and ontological elegance. However, each claim, when evaluated for its scientific utility in 1875, is found to be a qualitative vision awaiting a quantitative formulation. Clifford provides a new and powerful way of speaking about the world, but he does not provide the equations which allow one to calculate, predict, or test this world. The work's true value, therefore, is its performance as a conceptual seed. It asserted, with unparalleled clarity and 40 years of precedence, the fundamental idea that would lie at the heart of Einstein's theory of general relativity, the identification of the substance and dynamics of the universe with the geometry of spacetime. Clifford's paper stands as a monument to the power of pure reason to apprehend the possible structures of reality. Its claims were those of a seer, a philosophical physicist who, by following the logical implications of a new geometry to their ultimate conclusion, sketched the outline of a future physics with an accuracy that remains a source of scholarly wonder. It is a testament to an intellect that saw hills and motion in the very fabric of emptiness.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.